some, technical issues, we are happy to host Professor Stuart Raby from Ohio State University. He got his PhD in Tel Aviv University 1976. And he has over 40 years of experience in grand unified theories. This is the least to say because actually he is one of the main, developers of grand unified theories, and especially since the last 20 years, he has been pursuing like a program in grand unification theories and string theory. In particular, F theory. And, last July, there was this string phenomenology conference here in Dayton, and we wanted to catch some people, including Stuart Raby and Fernando Quevedo, but they left to early Korea. So this is our chance, and we are happy to hear you. So please start.
Okay, thank you for the invitation. I'm sorry for the difficulties. At any rate, I'm going to talk about a heterotic F-theory dual SU5 model. It's in collaboration with Herb Clemens, who's a distinguished algebraic geometrist at Ohio State University. I don't claim to be an algebraic geometrist, so we collaborate by me discussing the physics and him discussing how we can get this from algebraic geometry. And you see there are 5 papers that this talk is based on. In fact, there's extra one that this talk is based on. So let me start. So the outline of the talk is to discuss heterotic F-theory duality. I'm not sure if anybody is a string theorist there, so hopefully I'll try to give you some introduction. But if you have questions, you should ask. We're going to have an SU5 gut with Wilson line breaking, and that's a very important statement because it was said by many people that you can't break F-theory with an SU5 gut with Wilson line breaking without running into problems. And the problems we'll discuss in a second, there in fact are vector-like exotics. So we have a 4+1 split. I'll tell you what that means, but it means physically that there's an SU4 cross U1 X Higgs in the heterotic side, which breaks the SU E8 symmetry that we start out with down to an SU5 cross U1 X gauge symmetry. Typically, with Wilson line breaking, people found that they had vector-like exotics, and we solved that problem by having 2 sections instead of 1. We have gut breaking, which is non-local, which gives us precise gauge coupling unification. We also have a Z2 matter parity and a Z for R symmetry, and then I'll give you conclusions. And in fact, I'll give you the conclusions right now if you can't stay awake till the end. We constructed the global SU5 F-theory model with Wilson line breaking. We have 3 SO10 families of quarks and leptons and 1 pair of Higgs doublets, and no vector-like exotics. We have a Z2 matter parity and a Z4R symmetry, which I'll discuss in detail. We have these possible Yukawa couplings. I don't know if you can see my cursor, but we have these possible Yukawa couplings for quarks and leptons in terms of SU5 terminology. It turns out there are no observable proton decay, either at dimension 4, 5, or 6 in this theory. We have a complete twin sector, which is identical to the visible sector of the theory, except there are different scales associated with the gut scale and alpha gut. So let's discuss heterotic F-theory duality. On the heterotic side, we have an E8 cross E8 gauge symmetry on an elliptically fibered Calabi-Yau threefold. That means a torus fibered over a base B2 to get a Calabi-Yau threefold. E8 is broken to an SU5 cross U1 X gauge theory on the heterotic side by having a non-trivial, out of the E8 gauge group, we have a non-trivial SU4 cross U1 gauge bundle, which breaks the E8 symmetry down to SU5 cross U1 X gauge theory. We have 2 E8s, and in both E8s, this is what's going to happen. We then have a freely acting Z2 involution, which preserves the gauge symmetry, and the resulting Calabi-Yau threefold has a fundamental group, which is Z2 symmetry. In other words, you can wrap around the manifold once, and you don't come back to the original place. You have to wrap around twice to come back to the original theory. So there's a non-contractible loop that you can make on the manifold. On the X and Y coordinates are coordinates on the torus. And in the heterotic side, we have dx over y, which is the volume volume quantity on the torus, and dx over y goes to dx over y under the Z2 involution. The Wilson line wraps the non-contractible cycle and breaks SU5 gauge down to the standard model. And the Higgs data in the semi-stable, the Higgs data, which is this SU5 cross U1 Higgs data, in what's called the semi-stable degeneration limit, which is the heterotic limit of F theory, is defined in terms of two DP9, union of two DP9s connected along an elliptic fiber, and this gives you the Calabi-Yau threefold. And it also defines on the F theory side what's called the spectral cover. Is there any questions about what I'm talking about here?
I think I can follow, and there are people doing string theory following your.
Okay, good.
But if any student has a question, yeah. If not, I mean we can continue.
Okay, so let's continue. On the F theory side, we have an elliptically fibered Calabi-Yau fourfold over a base B3. B3 is a complex three-dimensional base or a six-dimensional manifold. And so you have the elliptic fiber, which is the same elliptic fiber as on the heterotic side. And the base B3 is given in terms of a P1, a surface, fibered over the same base B2 as on the heterotic side. The DP9s determine what's called the Weierstrass function or the Tate form. And I give you an example of the Tate form for an SU5 gauge group. So X and Y are the coordinates on the elliptic fiber, and A5, A4, A3, A2, A0 are given are functions on the base B3. Z is where the Weierstrass function actually has a singularity at Z equal to 0. And if I define T equals Y over X, this gives us, they're all functions on the base B3. The Z2 involution is freely acting on S gut upstairs, which is a K3 surface. And that defines S gut downstairs, which happens to be an Enrique surface with pi 1, the fundamental group on S gut downstairs, again, is Z2. The difference between... Yeah.
May I ask something? Sorry to interrupt.
Okay, no problem.
Is it very difficult to construct this kind of bases, the elliptically fibered Calabi-Yau form, or
the elliptically fibered Calabi-Yau fourfold is something that everyone does when they write down F theory models.
Okay, so this is a standard thing.
That's standard thing. And you can also define it with the Z2 involution, which is freely acting on the gut surface. The gut surface is a K3 manifold. And when you do a Z2 involution on K3, you get what's called an Enrique surface with pi 1 of S gut downstairs equals Z2.
So the base is standard?
This is all standard.
Oh, okay.
The actual manifold that we use is not standard, but this, what I'm telling you now, is all standard and was discussed in the literature by Beasley, Heckman, and Vapa, and by Donaghy and Weinhold.
Okay, thank you.
Now, in order to preserve the Calabi-Yau fourfold, it turns out that the elliptic fiber, the coordinates on the elliptic fiber have to take y goes to minus y. And this is different than was on the heterotic side, but the difference can be explained in terms of some algebra that I don't want to get into. So let me give you a picture of what's going on. We have a Weierstrass function, which is y squared equals x cubed plus f times x plus g. F and g are functions on base B3. Y and x, like I said, are coordinates of the elliptic fiber. And at a certain value, which is called when delta equals 0, it's a function of f squared and f cubed and g squared. When that vanishes, what happens is that the elliptic fiber has a singularity. And that happens when we define it so that happens at z equal to 0, so that the gauge group is some form of ADE classified gauge groups, and we're going to have an SU5 gauge group on the gut surface in B3. So this defines a two-dimensional complex surface in B3, which is defined by z equal to 0. And if you take that gut surface, and if you, instead of having singularities, you blow up these singularities in a way which preserves the Calabi-Yau fourfold, then what you get is a bunch of what we call sausages, and they describe the extended Dinka diagram of SU5. In other words, they have the same, they give you the same connections between alpha 1 and alpha 2, which is the intersection is -1, alpha 1 squared is 2, etc., just like the extended Dinka diagram of SU5. So let me discuss Wilson line breaking and the problems that you find with Wilson line breaking. And these were the problems which were expressed in two papers, one by Beasley, Heckman, and Vafa, and the other one by Donaghy and Weinhold, that says that y goes to, well, they said that you get vector-like exotics, which we're going to show that you also get. And when y goes to -y, what they didn't tell you is that you break the gauge symmetry. So let me discuss that in detail. And so by being able to do Wilson line breaking, we've actually solved the problem that they found. Okay, so we start again with the Tate form. And let me divide the Tate form by different powers of A0. So y over A0 cubed redefines y, x over A0 squared redefines x, z over A0 redefines z, and aj over A0 defines quantities we call Cj. The Cj's are they're all given by Casimir's operators of SU5. So this would be the quadratic Casimir of SU5, cubic, quartic, and quintic Casimir of SU5. There's no linear Casimir of SU5, because that would be given by the trace of the generators of SU5, which is 0. This is the equivariant, what they call the equivariant Kreppin resolution. In English, what that means is that it preserves the gauge symmetry. Kreppin means you blow up these singularities and preserve the Calabi-Yau fourfold, and that gives you these sausages. Under the involution, y goes to -y, that breaks the gauge group. If you take y goes to -y and take all the c equals 0, you have an E8 gauge group, and what happens is that the roots go to minus the roots. And if you take y goes to -y with an SU5 gauge group, these are the roots of SU5, they go to minus themselves, so the Cj's go to -1 to the power j Cj, and that breaks the gauge symmetry. So the first thing we had to do is solve that problem. By the way, this is all mathematical statement, but I'm not going to read it. I won't go through it. But let me tell you that this is a theorem by Narasim. You can read it yourself. Friedman, Morgan, and Witten used this to define the DP9s in terms of the data of the non-flat SU5 Higgs bundle on the heterotic side. And this was what defines what we call the spectral cover on the F theory side. But in order to do this, Friedman, Morgan, Witten process to define, given the data on the heterotic side, to define the data on the F theory side, it requires complex gauge groups with a choice of plus or minus I to define the complexification. So you really have a complexified E8 or a complexified SU5 that you're talking about. The summary, Z2 involution on the elliptic curve takes y goes to -y, and problem 1, the involution breaks the gut group because the involution takes the gut roots, rho complexified to minus rho complexified. And it turns out there's a simple way of solving this problem. Note the roots this is mathematical definition of the roots are defined in terms of the pure imaginary part of the complexified group. So rho C equals I rho goes to minus rho C, where rho are the physicist roots. So to solve this problem is very simple. In addition to what we define as the involution on the manifold, we have an action by conjugation on the roots. So rho C goes to I rho. In other words, when we do the Friedman-Morgan-Witten analysis, you have to choose a sign of I plus or minus I. So if we chose rho C equals I rho, and we do complex conjugation, that's just changing the sign of the complexification of the group, and that takes I rho to I rho, and hence I rho, the rho are unchanged. So we haven't broken any gauge symmetry by this flipping of the signs of the group of the roots back to their original sign. So let me go to problem 2. If you can see this, we have the cohomology tells you the number of states with these properties. So if we start out with SU5, if we want to break it down to SU3 cross SU2 cross U1, we get an octet of SU3, a triplet of SU2, and a singlet, which is hypercharge. And we see that we get one of each coming from the cohomology of the group. We have no chiral states, in other words, no matter type states, 8, 1, 1, 3, or 1, 1. But we do have, and we have no vector states, we get rid of them, so they're not there. But this is the vector-like exotics, and they're one of them, and they always exist as written down in these papers. The theorem says that these vector-like exotics always occur when you do an elliptic fibration with section, with a single section. And we proved that, in fact, in an old paper that we wrote down, because we didn't understand these papers. So we already found that we found these extra vector-like exotics, and you don't want to have them in the theory. The way Beasley, Heckman, and Waffe, and Donaghy and Weinholz solved this problem is by saying you have to have a non-flat hypercharged flux to break SU5 down to SU3 cross SU2 cross U1. You can do that, but when you do that, you break gauge coupling unification. The gauge couplings no longer unify at the gut scale because of the non-flat hypercharged flux. And I didn't like that, and so we're trying to solve that problem. So the solution to problem 2 is you have an elliptic fibration over a base B3 with 2 sections, given by the same Tate form of the Weierstrass function. The first section it's anywhere where the Tate form vanishes. So I've added this extra variable W, Y, and X, or the coordinates on the elliptic fiber. And the first section is when WXY equals 0, 0, 1. That's when the Tate form vanishes. So that, by definition, is the first section. And that's always there. So the Tate form W, Y, and X of the elliptic fiber, the torus, Z equals 0 defines S gut. That's where the discriminant vanishes. Z and AJ are functions on the base B3. And we make a choice. We say A5 plus A4 plus A3 plus A2 plus A0 equals 0. If we do that, then we automatically get a second section. This is given by this formula. And you can check that. If you plug that into the Tate form, you find out that the Tate form vanishes. Now we take W equal to 1, Y equals T cubed, X equal T squared, and Z equals Z over T. And that defines this quantity S. And this is what's called the spectral cover. And the spectral cover for us has a very special form. It breaks up. If you plug in that A5 plus A4 plus A3 plus A2 and A0 equals 0, you find out it breaks up as in terms of a 4 plus 1 split. And there are known consequences of having this 4 plus 1 split, which we didn't come up with, but lots of people came up with that consequence. But they didn't necessarily get it by this choice. So now our elliptic vibration has two sections, which are invariant under the initial Z2 involution. In the final definition of the involution, we include a translation by the difference of the two sections on the elliptic fiber. And it's that which gives us no vector-like exotics. And so when we do that, we find out that the vector-like exotics now are totally gone. If you can see my cursor, you see that there's zeros here for where the vector-like exotics were. Any questions? So that solved the problem of vector-like exotics, which means we can continue doing Wilson line symmetry breaking. Now, what does this 4+1 split of the spectral divisor give us? It says that in the initial E8, we broke the E8 down with an SU4 cross U1X Higgs bundle. That means the complement of this in E8 is SU5 cross U1X gauge symmetry on the gut surface. Now, the Z2 involution actually is an orbifold. There are fixed points. So the orbifold has fixed points on the base B3 and on B2 itself. So what's different from many other papers is that our gut surface, Z, is not necessarily stuck on B2. It wants to miss all these fixed points. And we do that by having Z in B3 and missing all the fixed points. So note, these fixed points are not Crepin, so they break the Calabi-Yau fourfold, but I was told by Jonathan Heckman that doesn't break the supersymmetry. And S-gut is in B3 and avoids all the fixed points. So that's something totally new in our model. Now, we want to choose the base B3 in a very special way so that we get 3 families of quarks and leptons and the right number of Higgses, meaning 1 pair of Higgs doublets. So we choose the base B3 equals P1 cross the base B2, and the base B2 is chosen to be a del Pezzo surface dP7. Now it turns out this choice has several nice properties. One, it is a unique del Pezzo surface with a finite discrete set of orbifold fixed points under the Z2 involution, which this was studied in detail by Blumenhagen et al. In this paper. So this dP7 was discussed by this group and shown that it has a finite number of orbifold fixed points under the Z2 involution and has the following properties. One, there are 3 families of quarks and leptons which come out of the cohomology of this system. And dP7 itself has a global symmetry, which is S4 cross S2. And it turns out that this S4 symmetry allows us to have a Z4R symmetry. So I want to discuss that Z4R symmetry next.
Diane, I have a question.
Go ahead.
Is it difficult to get these 3 families, or?
No, well, it's difficult in the following sense. You had to choose the right space. So if we chose dP6, we would not get 3 families. If we chose dP5, we would not get 3 families. So 3 families come because we chose dP7.
Okay, thank you.
So let me discuss the Z4R symmetry. We wrote this in a paper a very long time ago by Lee, Ross, Sheeran, Schmidt-Hoberg, and Vojravanga in 2010. And 2010. And what is it? It has charge. It's an R symmetry. So the superpotential goes to minus itself under the Z4 R symmetry. It's not invariant. And you do that by having charges for the 10s and 5 bars have R charge 1, the scalar fields, and the Higgses, Higgs up and Higgs down, have R charge 0. Now you should notice I'm not talking about any color triplet Higgses. So this would only work in higher dimensions other than 4, where you get rid of the color triplets. And in fact, we get rid of the color triplets by the Wilson line. It allows, the superpotential allows all these Euclid terms. It allows Euclid terms for leptons because the superpotential transforms with R charge 2. So this has R charge 1, this has R charge 1, this is 0, so it has R charge 2. The same for all the other terms in the superpotential that are allowed. And these are all the terms that you want in your effective low energy theory. Now, how would you break the Z4R symmetry? One possibility is if you get a non-zero vacuum expectation value for a piece of the superpotential, then that piece of the superpotential can couple to anything with R charge, total R charge 0. For example, a mu term has R charge 0, H up, H down term. And these dimension 5 operators, which mediate proton decay, also have R charge 0, plus 1 plus 1 plus 1 plus 1 is equal to 4, which is equal to 0 under a Z4R symmetry. So if you have a spontaneous breaking of the superpotential, gets a non-zero vacuum expectation value, that would generate a SUSY breaking, which gives you W0 has dimension 3 over M Planck squared, gives you the gravitino mass. And all of these terms then come, the mu term comes with of order M3 halves times some, perhaps some parameter. And the dimension 5 operators come as M3 halves over M Planck squared. And those are sufficiently suppressed to make dimension 5 proton decay unobservable. Now let me show you what defines the matter curves for our theory. The Z equals 0 and A5 equals 0 gives you the 10 curve. And upstairs, in other words, before you do the involution for this DP7, etc., we have H0 minus H1 is 6. We only want 3 families, but when we go downstairs, we break these into symmetric and anti-symmetric under the involution, and we only keep the symmetric terms, so 6 goes to 3 downstairs. Similarly, the 5 bar representation is given in terms of what we call A420, means A4 plus A2 plus A0 equals 0, and Z equal to 0. Again, has 6. And the Genos are given in terms of Z equal to 0 by themselves. Okay, so we do the involution. The involution now includes y goes to minus y, complex conjugation of the roots, translation by the difference of the two sections on the elliptic fiber, and we now also have the hypercharged elliptic Wilson line, which is flat Wilson line going around the gut surface. So downstairs, after the involution, we only keep the symmetric subspace 6, so 6 becomes 3. So that's a simplification of what we have. Here is exactly the results that we find. For the 10-dimensional representation, like I said, CUV happens to be what happens to these states under the involution. Let me go back. What happens to these states under the involution? Ly is the hypercharged Wilson line. So states can be either even or odd under the hypercharged Wilson line. They're either even or odd under the involution. And we found out that the H0, this is the cohomology H0, has 3 for the plus plus or plus plus minus minus or plus plus states. By the way, you can have plus minus states or minus plus states, but those are they all go away under the involution. We only keep the states which are even, totally even, under the multiplication of the involution times the Wilson line. So the states that we keep are the states that you want, and SU5 coming out of the 10-dimensional representation of SU5. So you have the quark doublet, the up bar, and the E bar states of SU5, of SU3 cross SU2 cross U1. These states, the conjugates of these are all 0, so you don't get any extra states. And so you have 3 families of 10s, of things which come out of a 10. And we also have 3 families of things which come out of the 5 bar, which we have the plus plus state and the minus minus state. Notice the quarks and the leptons, in both cases, come out of either a symmetric combination under the involution or an antisymmetric combination under the involution. So what happens exactly is you start out with, say, the 10. You start out with the 10 and you break under the involution, it goes to 10 even or 10 odd. Those are two different 10s. And the quarks and the leptons out of these states come out of two different 10s. And there are consequences of that. So we get three families of quarks and leptons. Let me finish that. It turns out we get one pair of Higgs doublets. So we have the minus, the doublet with charge -1/2 under hypercharge, or minus here with charge +1/2 under hypercharge. So we get one pair of Higgs doublets with equal and opposite hypercharge, but we get no color triplets because they don't exist in the low energy theory after the Wilson line breaking. Let me get back to this, the 10s and the 5 bars. Since the quarks and the leptons come out of different 10s or different 5 bars, there's no dimension 6 proton decay at tree level. So we not only have no dimension 4 proton decay because of the U1X symmetry, which I'll discuss next, we have no dimension 5 proton decay because of Z4R symmetry, and we get no dimension 6 proton decay at tree level. Okay, what about why we have no dimension 4 or proton decay violating operators? It's because the 4+1 split gave us a new charge, which is U1X. And the matter particles carried these charges under the U1X symmetry. 10s carry charge -1. The 5 bar matter has charge +3. The 5 of the Higgs has +2, and the 5 bar of the Higgs has charge -2. So the UNX symmetry allows these cubic Ucal couplings, 10 matter, 5 bar Higgs, or 10 matter, 5 Higgs. But the following 10 matter, 5 bar matter, which is an R-parity violating interaction at low energies, is forbidden by the UNX symmetry. We also find right-handed neutrinos in a separate paper. So we called them gamma -5. They have charge -5 under the UN symmetry, which is exactly what you'd expect by SO10. And so this UNX symmetry is actually coming from SO10 breaking down to SU5 cross U1. And this is the charge that a singlet would have coming out of an SO10 spinor representation. And then we found one state or one curve with charge +10. So that would allow these interactions, the right-handed neutrino coupling to 5 bar matter, coupling to 5 Higgs. So direct neutrino mass is allowed. But it also allows, because of this lambda +10, a Marana neutrino mass would be allowed if lambda +10 got a vacuum expectation value. Finally, under the Z2 involution, UNX is spontaneously broken down to Z2 matter parity. It's not spontaneous, it's explicitly broken by the UN involution down to Z2 matter parity. So we get a Z2 matter parity, dimension 4 operators, proton decay violating operators are forbidden. Z4R symmetry severely restricts the dimension 5 proton decay operators, and the dimension 6 operators are forbidden due to the Wilson line symmetry breaking. Okay, in terms of the string theory, where does the Z4R symmetry come? Well, the generator of the Z4R symmetry we call TUV. Okay, it has a Z4 symmetry. It's an odd symmetry because under TUV, the Tate form goes to minus the Tate form. It means the holomorphic 4 form goes to minus itself, and that corresponds to an R symmetry of the theory. The matter fields transform, they defined by AJ and Z equals 0 for the 10 and 5 bar. So they get charge under the Z4R symmetry -I because of that. At -I for AJ goes to A is J equals 0 and Z equals 0 gives an extra minus I. So the 10 and 5 bar matter fields have the TUV, or charge -1. Now, before I go on, let me say that the Z for R charge is given, these are all fermions, these define the fermions in our theory. The bosons are given by supersymmetry. So this is the Z for R charge of the fermions in the theory. This would be the Z for R charge of the gauge zeros. The Higgses come as quadratic in the A's and Z equal to 0, and so they have a different Z for R charge. So the fermions in the 10 and the 5 bar have Z for R charge -1. The fermions in the Higgs, or the Higgsinos, have plus I, and the gauginos would have Z for R charge -I. And this corresponds to I to the Q plus 1 for the fermionic components of a superfield. The bosonic components have charge I to the Q when theta prime equals -I theta under the Z for R symmetry. And this is exactly what we found in this paper. So now let me describe the low energy theory as much as we can so far. We believe that the visible and hidden sector have different scales associated with them. By that I mean different gut coupling constant and different gut scale. So the Einstein-Hilbert action is given in terms of some fundamental mass scale to the 8th power times the Riemann scalar integrated. It's a 10-dimensional Riemann scalar integrated over 10-dimensional space, which is Lorentz space R31 cross D3, integrated over 10 dimensions. So M Planck squared is just equal to M star to the 8th times the volume of B3. And if you're wondering what this delta is what we use to go from the F theory side with delta equals 0 to the heterotic side with delta equal to 1. And we actually want to understand the relative scales on the heterotic side. The gauge interactions are given in terms of this fundamental scale M star to the 4th, integrated. We have two gauge theories. We have the visible sector and the hidden sector gauge groups. They're defined at Z0 equal to 0 in both cases. The Z0 is complex, and then you integrate over 10 dimensions. So it turns out that alpha gut inverse, which would be the inverse, which was defined as 1 over alpha gut is the coefficient of these in 4 dimensions. So 1 over alpha gut is equal to M star to the 4th times the volume of the gut surface, either the gut surface for the visible sector, I equals 1, or the gut surface for the hidden sector, the twin sector, I equals 2. And the gut group is just given to the -4th power, is just given in terms of the volume of the gut surfaces, S1 or S2. So in the heterotic limit, which is called the stable degeneration limit, we have the base B2, but we also have the P1. And remember that our gut surface lives in B3, but not necessarily just in B2. So in the heterotic limit, the gut surface is a combination of B2 union with this P1, and the twin sector, the gut surface is the same B2 union with a different P1. And the two P1s come together, well, let me go back. The two P1s come together on an elliptic fiber, which defines this Calabi-Yau threefold in the end. So we have our base B3 union, the base B30 is B31 cross B32 is just the volume of these two P1s times the volume of B2. So the volume P1, A, P1B. The gut surface is this limit A equals infinity of B2 union with this P1. The gut surface for the twin sector is again this B2, which is the same union of this P1. So these B2s have the same volume. And we define Mi as the volume of P1, where I say I equals A or B, or 1 or 2. And then there's an additional quantity here, surface, which is we call C, whose volume doesn't depend on which gut limit are you in. So simply stated, the volume of the gut surface 1 or 2 is given by the volume of P2, B2, plus this volume of the P1s, the different P1s, times volume of C, and there's no reason why M1 or M2 have to be the same. Alpha gut times M Planck is just given by M1 plus M2 times square root times the volume of B2, so the square root of these, divided by the volume of B2 times 1 plus K Mi. So if you take alpha gut 2 divided by alpha gut 1, it's given in terms of 1 plus Km1 divided by 1 plus Km2. And there's, like I said, there's no reason why M1 and M2 have to be the same. And M gut 2 over M gut 1 is given by this quarter root of 1 plus Km1 over 1 plus Km2. So if you take the visible sector, have alpha gut inverse 24, and M gut equals 3 times 10 to the 16 GeV. If you take 1 plus Km, and this is just by hand, you'd have to, these are moduli in your theory, and you have to stabilize these moduli. But I'm just saying if we choose them in such a way that this ratio is 2.8, then M gut 2 is 3.9 times 10 to the 16 GeV. It's larger. And alpha gut inverse is alpha gut 2 is larger than alpha gut 1. Okay, so that's a possibility. We don't know how to fix these moduli yet, but let's just take that possibility and see where we can go with it. So there are at least 2 possible effective low energy theories that we have thought about. Any questions?
No, thank you.
Okay, so the first possibility is the twin Higgs VEV is 0 at the gut scale. That means, by what I just said, M twin gut is greater than M gut, alpha twin gut is greater than alpha gut. Thus, the low energy theory has a complete twin sector with twin baryons and twin leptons, which are heavier than the standard model baryons and leptons, which assumes twin Yukawa couplings are equal to standard model Yukawa couplings. We don't know that yet. Or the second possibility is that the effective twin theory, which has the number of, it's the standard model. So the NQCD is 3, the number of colors is 3, number of flavors is 6, just like in the standard model, 6 flavors of quarks. And it's described by Seiberg electric dual or magnetic dual because they're equal in the sense that the magnetic dual would have N colors equal to 3 and N flavors equal to 6 as well. So we can just write it in terms of a superpotential, which is the quark, anti-quark, or quark, these are all Weyl spinors, by the way, or superpotential. These are all superfields given in terms of Weyl spinors, Higgs up and Higgs down. And if the VEV of Higgs up and Higgs down are equal and equal to V, which is around M gut, which is a flat direction in this theory, all twin quarks and charged leptons would obtain mass at the gut scale. And the twin SU2 cross U1 is broken down to twin U1 electromagnetism at the gut scale. And the low energy theory only includes twin Higgses, twin Higgsinos, twin photon, and twin photino. Since there are no quarks below the gut scale in this scenario, the gut coupling constant, or the QCD coupling constant, twin QCD coupling constant, gets large at around 9 times 10 to the 13 GeV, which defines the lambda twin QCD. A consequence of that is that there could be a gluino condensate at that scale, which would break supersymmetry and give you a gravitino mass. I just arbitrarily chose some parameters of around 100 TeV. So this is a possibility where supersymmetry is spontaneously broken by a gluino condensate. And we had to worry, how do you generate a mu term? So a possible mu term can be generated using a Giudice-Masiero mechanism, which introduces in the Kähler potential a term which is the SUSY breaking VEV, let's call it S dagger, H up, H down in the Keller potential. S dagger gets a VEV. S dagger S would be the thing which couples to the gauginos, condensate, and break supersymmetry, and that would generate a mu term for your low energy theory. And it might generate a negative mass squared for the Higgs, which keeps the Higgs VEV at the gut scale after everything happens at low energies, as opposed to what happens in the visible sector. So I'm coming to the end now. We have Wilson line and the gut scale. The Wilson line wraps the gut surface. It breaks SU5 down to the standard model gauge group. M gut is equal to the compactification scale, or the guts, the size of the gut surface, 1 over the size of the gut surface. We have non-local gut breaking due to the Wilson line wrapping this non-trivial cycle. So we get precise gauge coupling unification, which would be a prediction of the theory. We get a complete twin world with scales fixed by the size of the twin manifold and the visible manifold. And we get mirror matter, which can be a dark matter candidate. So the conclusions are, we constructed a heterotic F-theory dual SU5 model with Wilson line breaking, something which was thought to be impossible before. We have 3 SO10 families and 1 pair of Higgs doublets, and no vector-like exotics. We have a Z2 matter parity and a Z4R symmetry. We have no observable proton decay in this model. We have a complete twin sector. And of course, there are many, many more open questions. So what are the future for this model? We don't know in fact, we don't know the number of right-handed neutrinos in either the visible or twin sector. We haven't determined that by the cohomology. We don't know if right-handed neutrinos get a Majorana mass. That would correspond to this lambda 10 getting a VEV, but we need to know the Yukawa couplings, and that's the next thing that we're working on. Of course, we would have to stabilize the moduli and SUSY breaking. Now, in the second scenario, that would occur due to this gluino condensate in the twin sector. By the way, if you have a gluino condensate in the twin sector, it breaks supersymmetry, but because of supergravity, the twin sector and the visible sector coupled to the same gravitino, that would break the supersymmetry in the visible sector as well. We don't know if orbifold fixed points in B3 break SUSY, although I spoke with Jonathan Heckman at Stringfino in Dijon, and he told me that he doesn't believe that it would break supersymmetry. We don't know which low energy theory we can have, which would be consistent with maybe inflation and cosmology. One possibility we worked on with Junichiro Kawamura was dark matter and a possible portal to the visible sector given by neutrinos. So this model provides a virgin theoretical laboratory. In other words, we're just scratching the surface and many hidden possibilities. And I thank you for letting me talk at this meeting. And let me tell you about a book that I wrote recently. And so that's the end.
Okay, thank you very much for the nice presentation. Are there some questions? No. Yeah, I have some questions. The first one is that I couldn't really understand the nature of the different scales from, let's say, the observational point of view. What would be the phenomenological consequences, if any?
Well, the phenomenological consequence is that you have a twin sector and a visible sector. They both have an SU5 gauge symmetry before you do the Wilson line breaking. But the gut group, the value of alpha gut and the value of M gut can be different. So alpha gut, the ratio of alpha gut in the twin sector versus the visible sector is given by the ratio of these P1s, the volumes of these P1s. So let me go back again one more. When you go to the heterotic limit, by the way, our gauge group is our z equals 0 lives on this surface. So it's a 4-dimensional or 2-dimensional complex surface, which is a combination of B2 and this P1 cross C. And our twin sector, the gut surface is this cross plus this. So because of these two different P1s, they can have two different volumes, and that can lead to two different sizes of the gut surface given by this formula. So Sy equals 1 or 2 can have different sizes, which determines what alpha gut is or what M gut is for these two different parts of the theory, the twin sector or the visible sector. Is that clear?
Yes, I think now it's clear. Thank you. Mm-hmm.
Are there any other questions?
No more. Well, I have also another question.
Go
And this
ahead.
regards because you know, I don't know F theory, so I just wanted to know if there are other groups where you can't combine with F theory, because yeah, I know this development of SU5, but
People
I don't know of other groups.
People have written down SO10 models from F theory.
Mm-hmm. And do they have? Mm-hmm.
Yeah, they have. That's in the literature. And but I think people have even written down SU5 cross U1. What is it called? The flipped SU5 theory, which is SU5 cross U1 from F theory.
I see. Mm-hmm. But I suppose that the constructions are very involved, but it is not easy to, from the phenomenological point of view, pin out some features.
Liliana,
right?
if I didn't have a algebraic geometrist with whom to work, I couldn't construct these models by myself.
Yeah, of course, I understand. But what I mean is that if there are some specific phenomenological fingerprints from each model, from which you can say, okay, the phenomenology goes in this direction or the other because of the different choice of gut group.
This would be the question of what is the portal to the twin sector. And in this paper by Junichiro, we discussed neutrinos as being the portal with the twin sector. And of course, we didn't know how many neutrinos there were in the twin and visible sector. So in that paper, we assumed just 3 right-handed neutrinos, which are identical in the twin and visible sectors. And they couple both to the active neutrinos in the visible sector and the active neutrinos in the twin sector. We assume that they get a Majorana mass at a high scale, and therefore the active neutrinos in the visible sector and what we call the sterile neutrinos in the twin sector are coupled. And so that might give you one way of understanding or prove, one smoking gun for this theory.
Mm-hmm. Okay, I understand.
But then the other possibility is what's the dark matter? If the dark matter, for example, if the twin sector gives you dark matter at low energies and the twin proton is 5 times heavier than the twin, than the visible proton, then if they have the same number density, you can explain why the dark matter is 5 times larger than the energy density of dark matter is 5 times larger than that of visible matter. But of course, you need to understand cosmology, and we're trying to do that.
Okay, I understand. Well, thank you very much for refreshing, a panorama, because I think I used to follow this kind of research, but it's already more than 10 years ago that I lost the track. So thank you.